Now let's talk about the Poisson random variable. The Poisson random variable is actually the limiting case of binomial random variable. Now consider this situation in the probability mass function of the binomial random variable here. If this size parameter n is too large, then calculating the number of combinations, which is n choose x, is going to get quite hard. And if p is so small, then p to the power x is going to be very close to 0, and 1 minus p to the power n minus x is going to be maybe very close to 1. So in that case, when p is very close to 0, okay, the success probability p gets too close to 0, and the number of trials n becomes too large. So we can take the limit of this probability mass function. And what happens in this case? You can see here, while n choose x can be a very, very large value to calculate, p to the power x can be very small. And obviously, multiplying a very, very large number with a very, very small number can yield quite significant numerical errors. And the power operations can take quite long time because p to the power x, if x is small, then n minus x is going to be quite large, and the power operations are going to take a long time. So let's see what happens if we take the limit of this probability mass function as n goes to infinity and p goes to 0. Now, in order to compute this limit, we basically make a change of variable, and we will say that, define actually, lambda equal to np, okay? And if lambda is equal to np, we can replace the success probability with p with lambda over n. So whenever we see a p here, the success probability is going to be replaced by lambda over n. And if p is replaced by lambda over n, then there is no need for this limit, p goes to 0. All we need to calculate the limit of this part where p is replaced with lambda over n as n goes to infinity. Lambda is basically an average value of np. As you can see, n is very large, p is very small, and lambda is simply a moderate value in this case. And we replaced all p values here as lambda over n and lambda over n here. Now, in order to take the limit, we are going to make some arrangements in this function. First of all, this lambda to the power x and x factorial here can be written in the same component, lambda to the power x over x factorial. So x factorial is taken here, and n to the power x here is taken here, as you can see. N factorial divided by n to the power x and minus x factorial. And here we have 1 minus lambda over n to the power n minus x. Because n and x, they are both integer values, we can simply write 1 minus lambda over n to the power n here and 1 minus lambda over n to the power x. Actually, n and x, they do not need to be integer values, but in our case, they are integer. And we can simply write it here. If we have a subtraction operation in the power, we can write 1 minus lambda over n to the power n divided by 1 minus lambda over n to the power x. Now, we have 3 components. Let's focus on the first component. If we take the limit of the first component as n goes to infinity, what happens? Now, n factorial can be expanded as n times n minus 1 times n minus 2, so on and so forth, up to n minus x plus 1 times n minus x factorial, and n minus x factorial components will cancel out. So in the numerator, there will only remaining these multiplier terms, and in the denominator, we will have n to the power x. Now, when n is comparatively very large with respect to x, there will be n terms multiplied in the numerator, which are very close to n, and we will have n to the power x. Again, these x terms, there will be x terms here and x terms here, and the numerator is also going to be very close to n to the power x. Therefore, as n goes to infinity, the limit of the first component is simply 1. The limit of the second component as n goes to infinity. Actually, we do not see any n here. Therefore, if we take the limit of the second component, we will get exactly lambda to the power x over x factorial. And for the third component, in the numerator, 1 minus lambda over n to the power n we have. And as n goes to infinity, we know that this formulation will converge to e to the power minus lambda from simple calculus. And in the denominator, we will have 1 minus lambda over n to the power x. As x is any value and n goes to infinity, lambda over n is going to converge to 0, and 1 to the power x is going to be converging to 1. Therefore, in this first, second, third, and fourth component here, the first component converges to 1. The fourth component here in the denominator converges to 1. All we have remaining here are these two terms. So as n goes to infinity and p goes to 0, the limit of the probability mass function of a binomial random variable becomes e to the power minus lambda, lambda to the power x over x factorial. We say that x is a Poisson random variable if it takes non-negative integers from 0 to infinity. Now, you see, Poisson random variable is the limiting case of the binomial random variable, and we know that binomial random variable has the maximum value, possible value, that is equal to the size parameter. If the size parameter goes to infinity, then the Poisson random variable can take any integer value. Therefore, the domain where we define the probability mass values of a Poisson random variable are non-negative integers. And a Poisson random variable can take the value of these non-negative integers with this respective probability, e to the power minus lambda multiplied by lambda to the power x over x factorial. Please notice that this lambda to the power x over x factorial is not a part of the power here, okay? So e to the power minus lambda is a term. This term is multiplied with lambda to the power x over x factorial. And a Poisson random variable cannot take any other value except the non-negative integers here. And in order to define this probability mass function, obviously lambda should be taking positive values. If lambda is 0 or negative, then this probability mass function will not be defined. Why? Because lambda was an approximation to n times p. It's an approximation of n times p, and n and p are both non-negative values in binomial random variable. Hence, we say that this probability mass function is valid only if the lambda here is positive. And this lambda value is called the rate parameter of the Poisson random variable, which means by different assigned values for lambda, by different positive assignments of lambda, we get a different Poisson random variable. And we say that this random variable x is a Poisson random variable with rate parameter lambda. Now, let us give some real-life examples of Poisson random variables. So where do we observe Poisson random variable? Actually, in practice, we can observe a Poisson random variable very, very frequently in real life. Okay? So an example that obeys the Poisson random variable is this. The number of people in Istanbul who survive to age 100. Now consider this. There are a very, very large number of people living in Istanbul. And for any person to survive to age 100 is a very small probability. So the number of Bernoulli experiments here is the number of people who lives in Istanbul. It is a very large number. The size parameter of this binomial random variable is very large. However, the success probability is very small. So in that case, when n is too large and p is so small, in that case, we can take the limit of the probability mass function and say that the number of people in Istanbul who can survive to age 100 should be modeled by a Poisson random variable instead of a binomial random variable. Actually, it can be modeled by a binomial random variable. However, the calculation of the probabilities are going to be quite complicated. So Poisson random variable, or defining a Poisson random variable, is a simplification to calculations of a binomial random variable. However, if n is not too large and p is not very small, okay, if any of these two conditions is not satisfied, you cannot approximate a binomial random variable with Poisson random variable. So we should be very careful here. Both n should be too large and p should be very small, so we can approximate a binomial random variable with a Poisson random variable. So let's give other examples. The number of misprints on a page of a book. So you can select a page of a book, and potentially there can be a misprint at every letter. And in any page of a book, there may be a very, very large number of letters written, okay? However, having a misprint in one of the letters is a very small probability. Therefore, the potential number of experiments is very large. However, the probability of having a misprint is very small. And if we assume independence in between the misprints, then we can say that a number of misprints in a page can be modeled with a Poisson random variable. Another example, the number of cars on Fatih Sultan Mehmet Bridge at 1 p.m. on any workday. Now imagine this. On any workday at 1 p.m. exactly, take a snapshot of Fatih Sultan Mehmet Bridge. How many cars would you see there? Okay, so why should we model this with a Poisson random variable? Now, how many automobiles are there in Istanbul? We should think about this question. There are many, many automobiles in Istanbul, okay? And the probability of any of these automobiles to be exactly on the Fatih Sultan Mehmet Bridge at 1 p.m. on a workday is a very small probability. So the number of cars which can be potentially over the Fatih Sultan Mehmet Bridge is very large. However, for any of them being there exactly at that time is a very small probability. Therefore, the number of cars on Fatih Sultan Mehmet Bridge can also be modeled by a Poisson random variable. See, all of these examples actually confirm the properties of a binomial random variable. However, we should model them with a Poisson random variable. So the number of wrong telephone numbers that are dialed in any day. So there are many people who are making telephone calls on any day. So the number of telephone calls made on any day is very, very large, infinite large. And for a person to make a wrong telephone call is a very small probability. And in that case, the number of wrong telephone calls made on any day is modeled by a Poisson random variable. Another example is the number of packages of a dog biscuit sold in a particular store each day. Now, we are talking about demand here. In a store, the demand to dog biscuits can be modeled by a Poisson random variable. Okay, as we are industrial engineers, it is obvious that we should be able to model the demand of products. Now, why it is modeled by Poisson random variable? There are many people entering and leaving a store on any day. Okay, so many people. But not everyone is interested in purchasing dog biscuits. However, in the end of the day, you see that some people have purchased. So there are many people entering and leaving the store. However, the probability of a person to be interested in purchasing a dog biscuit is a very small probability. Therefore, the number of people who purchase dog biscuits can potentially be modeled by a Poisson random variable. And we are leaving the other examples to you. You can see and read them in the lecture book as well. So let's solve a question about Poisson random variable here. The number of typographical errors on a single page of a book has a Poisson distribution with parameter lambda equals to 1. Lambda is called the rate parameter, if you remember. So the parameter of this distribution is 1. And we say that on any page of a book, we may have typographical errors, and the number of these errors is a Poisson random variable. So we calculate the probability that there is at least 2 errors on a randomly chosen page. So we choose a page randomly. What is the probability that there are at least 2 errors in this page? So say, let X denote the number of errors on the chosen page, and we say, according to the question, X is a Poisson random variable with rate parameter equal to 1. And we want to calculate the probability of X being greater than or equal to 2. We can calculate this probability using the probability of the complement event, which is the fact that X being less than 2. So probability of X being greater than or equal to 2 is equal to 1 minus probability of X being less than 2. And X is less than 2 means X can either be equal to 0 or 1. And these probabilities can be computed by using the probability mass function of the Poisson random variable. So lambda is equal to 1, e to the power minus lambda times lambda to the power 0 over 0 factorial. And here we have lambda to the power 1 over 1 factorial. And once these two values are computed, we can subtract the summation of 2 from 1, and we get 0.2642. This is the probability of observing at least 2 errors on a randomly chosen page. Now, let us calculate the expected value, the theoretical formulation. Okay, so if you are given a Poisson random variable with rate parameter lambda, lambda can be any positive value, how do we compute the expected value of this Poisson random variable? Now remember, for discrete random variables, we calculate the expected value by multiplying the potential values that it can get with the respective probability masses. So X is multiplied with the probability mass function of the Poisson random variable. And these values should be summed up. However, in this summation, there are infinitely many terms from 0 to infinity. Now, how do we solve this? So let's do this trick. Again, when X takes the value of 0, this product is going to be 0, and it is not going to be effective in the summation. So we start the sum from 1. And if this summation starts from 1, then you can see that in the numerator here, lambda to the power x, there will always be at least 1 lambda value. So it is going to be a common multiplier, and this common multiplier, lambda, can get out of the summation. And the remaining term, lambda to the power x minus 1, can be written here. Again, e to the power minus lambda is independent of the changing x value. It can also be taken out of the summation. And we will have from 1 to infinity the summation of lambda to the power x minus 1 over x minus 1 factorial if x and x factorial here cancels out. Now, if we apply a change of variable here, if we say that I is going to be equal to x minus 1, whenever we see x minus 1 here, we can write simply I, and this summation is going to be changed for changing I values from 0 to infinity. And the summation is going to be equal to e to the power lambda. So where do we understand it? Actually, we know the fact that the summation of the probability mass values should be equal to 1. Therefore, the summation of this term should be equal to e to the power lambda. And then this e to the power minus lambda and e to the power lambda cancel out, and we get lambda simply. Now, you can easily see that the expected value of a Poisson random variable is equal to lambda. Why? Actually, in the binomial random variable, where we have the number of trials equal to n and the success probability of each trial equal to p, we have said that the average number of successes that we are going to observe is n times p. And Poisson random variable is a limiting case of the binomial random variable, and lambda was a replacement for np, actually. Therefore, if the binomial random variable's expectation is np, then the Poisson random variable's expectation will simply be lambda. And that's it. Actually, without using any hard calculations, we can use this logic to determine that the expected value of a Poisson random variable is lambda. So let's solve this question. The number of false fire alarms in Maltepe averages 2.1 per day. So it says, on the average, we observe 2.1 false fire alarms in Maltepe on any day. Okay? And this is simply the average value. So this means on some days, we may observe no fire alarms, and on some days, we may observe 4, 5, 3 fire alarms. But the average value is 2.1. The question follows like this. Assuming that a Poisson distribution is appropriate, what is the probability that 4 false alarms will occur on any given day? Okay, so on any day, the number of false fire alarms follows a Poisson distribution, and the average is 2.1. This means what? If the average is 2.1, if we use X to denote the number of false fire alarms in Maltepe, then the expected value of X is equal to 2.1. This is said by the question. And for a Poisson random variable, expected value is equal to lambda. So this first sentence actually states that lambda is equal to 2.1. So at this point, do not forget to write the unit of this rate parameter. So this rate parameter has a measure of speed, alarm per day. Okay, these things are important. Okay. And Poisson, X is a Poisson random variable where the rate parameter or the mean of X is equal to 2.1. And we are interested in calculating this probability, the probability that 4 false alarms will occur on a given day. That is equal to probability of X being equal to 4. And basically, we use the probability mass function of Poisson random variable, and we plug in lambda value as 2.1 here and here. And because X is going to be equal to 4, we plug in 4 values in place of X here. And once these values are calculated by the means of a calculator, you will get 0.0992 as the probability. Now, we compute the variance of the Poisson random variable. So how do we do it? Now, suppose we have a Poisson random variable X with rate parameter lambda, and here the statement says that the variance of this Poisson random variable is also equal to its rate parameter. So the variance is also equal to lambda. Why? Actually, we can answer this in a very, very simple manner. Again, the binomial random variables variance was n times p times 1 minus p. And we replace n and p with lambda. And there is 1 minus p. However, p is very small. Okay, because Poisson random variable is the limiting case where p converges to 0. And 1 minus p converges to 1. Therefore, the Poisson random variables expectation and variance should be equal to each other. However, we can also calculate the variance of a Poisson random variable by the convenient formula of the variance by subtracting the square of the expectation from the expected value of x squared. So we need to compute the expected value of x squared. So let's do it. For all potential values for the random variable to take from 0 to infinity, x squared must be multiplied by ae to the power minus lambda times lambda to the power of x over x factorial. And now let's do our first trick. If x is equal to 0, then in this case, the term that's added in the summation is not going to be effective. So let's start this summation from 1. Okay, x squared times e to the power minus lambda, lambda to the power x over x factorial. Now, take one of the lambdas outside again. So there remains the remaining terms here. And we have x squared here. Let's cancel one of the x's with the first multiplier of the x factorial. So there remains x over x minus 1 factorial. And here we are going to apply a change of variable again. We are going to say that I is going to be equal to x minus 1. Therefore, as x changes from 1 to infinity, I should change from 0 to infinity. And whenever we see an x minus 1 value here, we replace it with I. Whenever we see an x value here, we replace it with I plus 1. Now, I plus 1 here and the multiplier here can be distributed in the summation. So this summation can be expressed with these two summations. First, we multiply here with I in the summation and multiply here with 1 in the summation. And this term is basically the expected value of a Poisson random variable, because the Poisson probability mass function here is multiplied with the potential values that the random variable can take and summed up. And the expected value of a Poisson random variable is lambda. And this term here must be equal to 1, because this is the summation of all probability mass values for a Poisson random variable. Hence, the term here should be equal to lambda plus 1. Therefore, expected value of x squared is going to be lambda squared plus lambda. And we subtract the square of the expectation from this component. This means lambda squared from lambda minus lambda squared. If lambda squares cancel out, you can easily see that variance is also equal to variance. The variance is also equal to expected value lambda. So let's solve another question. Service calls come to a maintenance center according to a Poisson distribution and on the average 180 calls per hour. We need to find the probability that no more than 4 calls come in any minute, fewer than 2 calls come in any minute, and we also need to calculate the variance of the number of calls per minute. Okay, now in this question, if you realize that the questions are always asked in the minutely terms, okay? No more than 4 calls come in any minute. Fewer than 2 calls come in any minute. So, however, the information about the Poisson random variable is given in the hourly units. Now we need to be very careful, okay? So, we need to say that x is a Poisson random variable with rate parameter equal to 180 calls per hour. 180 calls per hour. However, because the questions are asked in minutely units, we need to convert this rate parameter 180 calls per hour into minutely units. Which means if on any hour the average number of calls is 180, and there are 60 minutes in an hour, the average number of calls in any minute must be equal to 108 over 63. Therefore, you need to define your Poisson random variable according to the time unit that is given in the questions, which is minute. So x is going to be Poisson distributed with rate parameter lambda equal to 3 calls per minute. Now, let's answer the first question now. What is the probability that no more than 4 calls come in any minute? Which means, what is the probability that the number of calls in any minute being less than or equal to 4? So we are going to sum up the probability masses for all integer values from 0 to 4. And the probability mass function is here, and the rate parameter is defined as 3. So we need to sum these terms up for x changing 0 to 4. And as you can see, e to the power minus 3 is a common multiplier, which can be first calculated and taken out of the summation as 0.0498. And the remaining terms, 3 to the power x over x factorial, is going to be equal to 1 when x is equal to 0, 3 when x is equal to 1, 9 over 2 when x is equal to 2, so on and so forth. And once everything is calculated, you can see that the probability of having no more than 4 calls in any minute is going to be approximately 0.8153. The second part here, it asks fewer than 2 calls come in any minute. The probability that fewer than 2 calls come in any minute, which means the probability of the number of calls in any minute being less than 2. And this includes only 2 probabilities, the probability of having no call and probability of having 1 call in any minute. So we are going to sum the probability mass functions by plugging in 0 and 1 values in place of x. And here, the probability is going to be equal to 0.1991. For the third part of the question, it says, what is the variance of the number of calls per minute? If the number of calls per minute is modeled by a Poisson random variable with rate parameter equal to 3, its variance is also equal to the rate parameter, that is 3. and its expectation is also equal to 3.